Problem. Mhm. One second. I made you a host, not a co-host, so it's a problem.
Okay.
So I have to undo that because
Can I change it?
yeah, you have to change it because otherwise when we record. Okay, so now I'm recording. Sorry. Okay,
Okay.
hello, thank you. Hello and welcome to the New York City Category Theory Seminar. Welcome. Today, Thomas Gonda. Oh, so this is our first talk of the fall 2023. Thomas Gonda is going to be talk about a framework for science universality in physics, computer science, and beyond. Thomas, take it away.
Thank you.
Thank you all for
So,
coming. Where it's a special time. Thank you all for coming. It's
yeah,
good.
thanks for being here at the unusual time. So, I was born in Slovakia at a town called Michalovce, and then I did my bachelor's degree in Edinburgh. That was in maths and physics. And then my PhD was in Waterloo, Ontario, in Canada, in physics. And now I work as a postdoc in Innsbruck at the group of Gemma de las Coves. Um,
I've never heard somebody more international than that.
yeah,
Very good.
I've been around.
Very nice. Good. Good
Um,
for you.
yeah, so this work that I will be telling you about is indeed a joint work with Gemma de las Coves and also Sebastian Stengele and Tobias Reinhardt. And you can now find it in an archive under the handle you can see there. And in the paper, there's many more details than I can cover today, but I will try to give an overview of what we did. So indeed, this is a framework for universality, but first of all, because we are a category theory seminar, I have to say that this is not about universality in the sense of universal constructions in category theory. And I will give you a bit more detail on what kind of universality we have in mind.
I just want to
So
say it's 70 pages. It's a big paper. It's a very
it's a
big
big
paper.
paper. Yeah.
It's got a lot of good stuff in it. Good.
Okay. So here are a couple of references I will refer to throughout the talk today. Um, and yeah, I will come back to them later. But first of all, I want to start with some motivation for why we are trying to do this in the first place. We have a couple of examples of universality that we would like to understand better, maybe generalized and understand from like a more abstract perspective. And these are the two primary ones. So the first one is that of universal Turing machines, which I'm sure many of you have some idea about. And the second main example is that of universal spin models, which is probably new to most of you. It's a more recent work, which indeed Gemma de las Coves has been involved in. So these are the two main examples. I will get into more detail later. There's a couple of other examples that we also are inspired by, but maybe not always at a technical level, but maybe more at a conceptual level. We have some other examples from mathematics, but also ideas from biology, organic chemistry, and philosophy. But in this talk, I will just focus on these first two examples, which are the key, also in building this whole framework. And then the aims that we have in terms of what we want to achieve is to build a kind of general language that can unify these different types of universality that appear in different domains. It should be a language that can express these examples and kind of organize what we know about the different types of universality. And we achieve some part of this goal. In particular, we build this framework and we have some general statements, some general theory that we can express in terms of it. So, for example, we can express when is universality in a formal sense, trivial or non-trivial. We give necessary conditions for when universality can appear. And we also find a relation between universality and a notion of undecidability within this language by expressing a fixed point theorem in the framework itself. So we will get to that later. First of all, let me start kind of going back to the examples and giving a little bit more flesh on them. So universal Turing machines, they are a kind of automata. So what does it mean? We have an automaton which has this head and sits on a string of characters. So this is the input string on the left, which we denote by C, let's say. And the Turing machine is an automaton that can change the values of the tape, and at some point it may halt, may find an internal state that's the final state, and at that point we think of the current value of the tape as the output of the Turing machine, and we will think of this as a particular function, an evaluation function that takes two inputs. One of them is the Turing machine, the other one is the input tape, and the output is going to be the output tape. So this is the evaluation of a Turing machine on particular string. And the universality of such an automaton means that this universal Turing machine can, in some sense, emulate any other Turing machine there is. So what does it mean to emulate it? Well, this is expressed in the equation at the bottom right. So there, on the right-hand side of the equation, we have the evaluation of some arbitrary Turing machine T, which gives us a particular computable function from inputs to outputs. And on the left-hand side, we have an evaluation of the universal Turing machine, which is fixed, but not on any input, but in particular, this input includes a program P, which is a description of the Turing machine, little t. So in this sense, if this program exists, this description of T exists for every Turing machine, then U is said to be universal. It can emulate the behavior of any other Turing machine. Something similar is going to appear in the case of the spin models. So let us go a bit into detail of the universal spin models. So first of all, we need the notion of a spin system. So spin system is going to be we can think of it as a model of a complex network that has some constraints, or it could be a model of a system of interacting particles in physics. So what are these interacting particles? So we will have a hypergraph whose vertices will be the individual particles, and for each of them, so each particle in V, we have a local degree of freedom. So for us, the degree of freedom will be sigma, just some finite set of possible states, of local states for this degree of freedom. And then the edges of the hypergraph are going to tell us about the interactions between these particles. On top of that, we have a particular energy function, the Hamiltonian in physics. So this is a real valued function from possible configurations of all the local degrees of freedom that outputs the energy of that configuration. And in particular, it's not just any function, but it has to be a function that is a sum of local coupling terms. So for each of the edges, for each of the local interactions, we have a particular coupling term. And then when we sum them together, we get the total energy. And from that energy, a lot of interesting properties of the system can be extracted. Here's an example. So you can think of a hypergraph which is on a plane, on a 2D lattice, let's say, where the edges are such that each vertex has an edge of its own, and then also each pair of nearest neighbors has share an edge. And this is what is called a 2D Ising spin system. In this case, for the Ising spin system, we usually take each local degree of freedom to have just two values. So that would be either 0 or 1, usually. And then the Hamiltonian function is given by this sum, where you sum over each of the local terms with some local magnetic field. That would be this Ri. And then for each of the nearest neighbors, you also have an interaction term between them with a particular form. And if you take all the possible 2D Ising spin systems of this type for different sides of the lattice, different interaction strengths, different local fields, this would be what we call the 2D Ising spin model. So the spin model is a collection of spin systems of a particular type. So in this case, the type would be that they are all on a 2D square lattice with this particular interaction type. But there are other spin models as well. This is a particular simple one because we have very restricted type of interaction, and it has to be a planar one as well. What's perhaps surprising is that the whole complexity of behaviors of spin systems that can be quite wild in a sense can be, in a certain well-defined sense, emulated by these 2D Ising spin systems. And this is indeed the statement of universality of the 2D Ising spin model, which has been proven in this paper of Velasquez and Cubitt. I cannot really go into the full details of that statement, but what they show is that if you take any spin system, in particular, it could have many dimensions, it could have very non-local interactions, and so on. You can find a particular embedding of it in a 2D Ising spin system, possibly with some additional degrees of freedom, additional local variables, and also an embedding of the interactions of this potentially complicated or generic spin system on these 2D square lattice interactions, such that the behavior of the generic Ising spin system matches the behavior of the 2D Ising spin system when you fix these extra flag variables. And it's not just...
Now, there's one difference. A Turing machine is a single Turing machine, and here you have you have to say that, or you have to. Okay, go. Sorry.
Yeah, indeed. So before we were talking about Turing machines, and there is a single universal Turing machine that can emulate all the other ones. Here we are talking about spin systems being simulated or emulated by a class of spin systems. So this class is the 2D Ising spin systems. And indeed, this is a difference between the two scenarios. And in our framework, we will see that as a particular difference that appears, but we also have a way to talk about them somehow at the same level. That will appear later. Okay, but that's as much detail as I would like to go to in terms of the spin systems. One thing that maybe should be mentioned is that this way of simulating a generic spin system on the 2D Ising is not arbitrary, but it satisfies some particular scaling in terms of the parameters. But that's going into those details would not be really so relevant for this talk. Okay, so now having introduced those two examples, let's move on to the framework, so to say, and describe how the setup within which we will try to understand these examples more generally. First of all, I already said that between these spin systems, like taking a generic spin system and emulating it on a 2D Ising one, we have some constraints that are placed on the simulation. And these constraints, we need to be able to express them somehow. And we do so by choosing a particular ambient category. So this is not a technical term. Ambient category just means it's a category that you have to choose that will specify the constraints or what is a valid emulation of a generic target element with this universal one, let's say. This category will satisfy certain properties. In particular, we want each object to come equipped with a commutative comonoid, and this will allow us to share variables between different inputs. This was also called a data service in some works of Duško Pavlović, for example. Or some authors also call it a GS monoidal category for garbage share. So there's an element, so there's the counits, the discarding, and then there's the comonoid, the comultiplication, which we interpret as a copying operation. We'll see some examples later on, but for now you can think of the category of relations or category of sets and functions as the kind of simple examples of such a structure. Given this structure, we can now talk about different types of morphisms. The ones that will be particularly important are the functional morphisms on the left. And these are indeed, in the case of the category of relations, these would be the functional relations. So they're the ones that are at most single valued. And then the total morphisms that satisfy the equation on the right, these would be morphisms that are, in some sense, everywhere defined, or for the case of relations, these are the total relations. And if a morphism satisfies both of these conditions, then we call it deterministic, which for the case of relations would be that it's a function. With these definitions, we have a few other concepts that we will need. So there's the notion of each morphism we can associate a domain, which we in some sense think of as a morphism on the domain of the morphism of this morphism, which is a bit weird to say, but it just means that it's a set of elements. If we think of this as a set where the function or the relation is defined. So indeed, if f is a relation in the category of relations, then the domain of that relation would be the set of elements of the input where the relation is defined. And using this, we can then express a notion of when one morphism extends another, or in other words, when, for example, f in this case agrees with morphism G when restricted to the domain of G. So here on the left-hand side of this equation, we have f, which is restricted, which is precomposed with the domain of G, and on the right-hand side, we have G itself. This gives us a preorder relation between morphisms that tells when, in some sense, the two morphisms are the same when we restrict to the smaller domain, but one can be also defined on other inputs. Okay, so this is a lot of definitions, but we need it in order to even state somehow the basic setup of the framework. So the framework is given in some sense by what we call a target context category. So this is the ambient category, which specifies these allowed simulations. It is equipped with a particular choice of two objects. So this is object T. We already saw it as the set of Turing machines, or it will also be a set of spin systems. An object C. These we call the contexts. And then also a preorder relation, this funny big relation, which for the time being, we'll see some examples of it, but for the time being, you can think of it just as being equal to this extension relation that we saw on the previous slide. There are some axioms that we needed to satisfy in order to be able to then prove some results about it, and these are indeed satisfied in all the examples that we have. So how does this abstract formalism relate to the two examples that we had? Well, first of all, let's go for the Turing machine case. There, the ambient category, we call it comp of naturals, is in a certain sense a category of computable functions, where an arbitrary object is a power of the naturals. Morphisms between them are going to be computable functions or multi-computable functions with multiple inputs and multiple outputs. The object T is the set of Turing machines, but in particular, it's a particular choice of an enumeration of Turing machines. Set C, the context, these are going to be indeed the input strings, which are also identified with natural numbers for a finite set of characters. And then the relation between morphisms from A to T cross C, so target times context, is just a relation that expresses when the two Turing machines compute the same output on a given context. So, for example, if I'll not say more about that. It tells us whether two Turing machines on a given context are giving the same output or not. Now, just to give another example, let's look at the spin systems. So in that case, the ambient category we call the rel poly. So this is going to be, in some sense, category of bounded relations, where each object is a set, but not just a set. It also comes with a so-called size function. So each element of the set is associated with a particular size, which could be in a real number. In our case, it's just a natural number. In particular, for example, for the spin systems, it's going to tell us about the number of parameters that we need to specify to get the Hamiltonian. So it tells us about the size of the configuration space. The morphisms between these size sets are going to be relations, but in particular relations for which the size is bounded by, in our case, a polynomial function. So the size of a particular element of a set cannot increase by more than a polynomial under this relation. And the targets that we want to emulate, so before there was Turing machines, here it is an arbitrary spin system. So this is the set of spin system with this notion of size that I mentioned. And then the context in which somehow we are looking at the behavior of this spin system in some context. So this context would be particular configuration, the local degrees of freedom. And then the relation between these, let's say, a given spin system and a given spin configuration is just expressing that their behavior is in a certain sense equivalent, which includes the fact that their energies, so the Hamiltonian functions, when evaluated, are the same, but there are some additional conditions that I will not get into details, but you can have a look in the paper or ask me later. So these are the two main examples. There's a lot of moving parts, but in order to get to some of the general theory, let's move on now. Okay, so here we had this kind of background of the whole framework, but now in order to talk about whether there is universality or not, we look at particular morphisms in this category, and these are what's called simulators. So a simulator is a particular morphism of this type. It has two inputs and two outputs. One of the inputs, P, we interpret as programs. So this would be indeed, in the case of Turing machines, the programs that we apply to the Turing machine. The other input is a context. So that would be an input string in the Turing machine case. And then there's two outputs. One of the outputs is a target. So let's say a Turing machine, and also a context. So these two morphisms that appear in the definition or in the somehow expression of the simulator is the compiler, which takes a program and it generates a target. And then the other is the context reduction. So let's look at some examples to make this more concrete. One example which always exists is the trivial simulator. So this would be just an identity function, in which case the programs and the targets coincide. So this is, in some sense, a simulator that expresses the totality of all targets. And we will use it in this sense. So, for example, when we make statements about universal Turing machine being able to emulate all other Turing machines, so this all other Turing machines will be expressed by a trivial simulator. So trivial simulator we can think of as any Turing machine in any context, or indeed any spin system in any context. It would mean in a particular configuration. So this simulator always exists, but then there are some, of course, many others. For example, given a particular Turing machine, that's denoted by U in this case, so that's this triangle is a particular morphism which just denotes an element P, Turing machine. The compiler for this singleton simulator is given by the constant function. It takes a program, it discards it, and then outputs this Turing machine. So this is in the case of a universal Turing machine, that would be the universal Turing machine that we use to emulate all the other ones. It's somehow our choice of the target that we want to use. And then the context reduction, it just takes a program and an input string and combines them together into a single string. So for example, that could be done by many different functions, but maybe we could take a program and then append a symbol that separates it from the rest of the input and put them together into a single tape. This is the singleton simulator for a Turing machine. And in the case of the spin systems, I don't have it here, but there indeed, as Nosson was mentioning, there we would not want it to be a singleton simulators because we may want to use different 2D Ising spin systems to emulate different generic spin systems. In that case, this compiler function or relation would not be a constant function. So that's kind of the difference between the two cases, that in the case of Turing machines, we can find what we will soon define to be a universal simulator, which is singleton, where the compiler is a constant function. But this is not possible for the spin system. So in the spin systems, this compiler will have to be a non-constant function, which is nevertheless going to have its image within the special class of these 2D Ising spin systems. But indeed, there's a difference between them because one is constant and the other one is not constant. And in fact, cannot be constant. Okay, so this is somehow the key object that we are now studying, the simulator. And one could say that what we want to study about it is this property of being universal. So let us now go to this notion of universality for simulators. In order to express it, we need a notion to compare different simulators. And this notion of comparison is in terms of reduction. This is a notion that comes from computer science. It's somehow inspired by the Turing machine example. And so indeed, a lax reduction between two simulators, S and S primed. Here I just denote them by a single box, but you can imagine them being somehow decomposed into these two parts, as on the previous slide. It's just a particular morphism between the programs of one simulator and the other, such that they are in this relation. So if we think of these as being total morphisms, so everywhere defined, and this relation as equality, which is often the case on the domain, then it would just be saying that the simulator S, when we precompose the reduction, so we relate the programs of S prime to the programs of S, it just reduces to the behavior of this S prime simulator. And that with this notion, we then define universality of simulator to be the property that there is such a reduction from this simulator to the trivial simulator. So ID stands for the trivial simulator. And so the existence of this reduction is expressing this fact that the behavior of the universal simulator can emulate all targets in all contexts, which is expressed by this trivial simulator on the right-hand side of the reduction. So, I mean, this is quite abstract, especially with so many definitions that I have introduced. But let me give you some examples of simulators that are universal. So first of all, every trivial simulator is universal, trivially in some sense, because we can just apply the identity reduction and find a morphism between a trivial simulator and itself. So in some sense, the fact that there exists a universal simulator in our framework is not an insightful fact. The trivial simulator is always universal, and the way we interpret this is that if one has access to all the targets in all the contexts, then one can indeed simulate all the targets by just using every single one of them. So this is some sort of trivial universality, but it's not the one that we are interested in ultimately. The other example is indeed this singleton simulator that I briefly introduced, but in particular only for a universal Turing machine. And one can indeed show that it is such singleton simulator in the target context category of Turing machines is universal if and only if the corresponding Turing machine is universal in the standard sense. Another example of a universal simulator would be the 2D Ising spin model with fields. So I didn't give you the details of that simulator, but we talked briefly about it. The compiler takes a particular, some generic spin system and associates to it a 2D Ising spin system, which is potentially much larger, but has to be bounded in size by some polynomial because of our ambient category. And the context reduction implements a very specific reduction on the configuration. But it's quite a complicated construction. There are some other ones. So for example, an NP complete language can be seen as universal for NP problems. A dense subset can be seen as being universal for the superset that it's a subset of. Generating set of an algebra is universal for the set of tuples and formulas. And and there are some other ones as well. Universal Borel set I didn't mention here. But in some sense, the Turing machines and the spin models are the key examples in here. Is there a question?
Yeah, before you go on, does everything
Yeah.
work out with the NP complete language? I mean, that's interesting that every single NP language or can be reduced. That's what you say.
Yeah, I would say the example of completeness for a computational complexity class, so it would apply not just NP but more generally, is not as insightful as we would like. So we can express it in the framework. Um, However,
What
the data
what
that
fails? Mhm.
I wouldn't say it fails. It's just in order to use the framework to learn something about that example, you would presumably want somehow the data of reducing one language to the NP complete one to be somehow accessible from the simulator itself. And this is not the case. So I would say the example, we can express it in the language, but it's not clear how much we can learn from doing so in present.
Right. So the reductions have to be polynomial as opposed to just computational.
Hmm.
Mm.
Yeah, indeed.
Okay, thank you.
Okay, so those are examples of universal simulators, and in the remaining time, I will try to go into a bit of the general theory of what we can learn about universality. I have to pick what exactly to cover, but one thing that we can show is a no-go theorem. So it's a result that tells us in what situations we have, in some sense, no hope of universality. So that's in the context of a particular simulator. So here's a simulator for the spin systems. So the targets are spin systems. The compiler maps the generic spin system to the Ising one, and the reduction just expresses reduction in the configurations. The theorem says that if you have a function from the target to real numbers, so here we can think of not necessarily T as an object in the category, but maybe a set of deterministic states, and T is the set. And this function is in a suitable sense monotonic with respect to this big ordering. Then what you find is that whenever S is a universal simulator, then somehow the upper limit on the values of this function on the right is bounded by the upper limit on the value of the function only on the image of the compiler. This is the image of the compiler here. And indeed, what you find, for example, if you choose this function to be just the size of the spectrum of a spin system, so that would be the set of possible energy values that the spin system takes. Well, in that case, you can prove this monotonicity, and you find that the right-hand side is unbounded. So there's no, because these spin systems are of arbitrary size, they can have arbitrarily large spectrum. However, if you want them to be finite, so still finite hypergraphs with finite number of degrees of freedom, then the left-hand side uh, uh, cannot be infinite unless indeed this compiler function has also unbounded image. So what is saying is that in order to have a universal spin model, you need this infinite number of elements in the compiler. And so in particular, it's saying that for the spin systems, you cannot have this situation like in the Turing machines where we have a single Turing machine that emulates all the others. Here we need at least, we cannot do with any finite number of spin systems. Unless, of course, you would include perhaps continuous spin systems, but this is not what we do at least we don't even know how to do it in the framework. Okay, so that's one result about absence of universality. And now I would like to spend some time on this fixed point theorem and how we can find a relationship between particular type of universality and a notion of undecidability in our framework. Okay. So in order to do this, there are some details in place, and what we find is that this framework, as I expressed it, as I introduced it, is not quite sufficient. We need to add additional pieces of structure. And I don't want to go into the full details, but here's a kind of schematic description of what we need. So on the left-hand side is what I described to you roughly. So that's the ambient category with targets, context, and so on. So this is somehow the abstract description of the ways of simulating between different entities. And on the right-hand side, we have what you could call is like a concrete description of these abstract processes that sits within the category of relations. So this is like a concrete interpretation of these abstract processes as relations. So there will be a particular set of targets now, really, a set of contexts. And on top of that, we also have now explicit behaviors and an evaluation function that takes a pair of a target and a context and outputs a behavior. So indeed, this kind of mimics the example of the Turing machines, where if we go back to that slide, we have this evaluation function, which takes a Turing machine and an input string and generates the output string. So this would be the example of the evaluation function for the Turing machines. And there's a similar notion for the spin systems as well. But somehow we need this additional piece of structure in order to talk about these fixed point theorems, as we'll see. Okay, so in the two examples that we mentioned, the targets and context are the same as before, but what we have additionally is these behaviors. So for the Turing machines, that would be just the possible output strings. For the spin systems, these behaviors, they will include the information about the energy of a particular configuration of that spin system. But there's some additional information that we need. So in particular, there will be the spectrum of the spin system and also some threshold on the energy. That's needed for some technical details. And then, so if we go back to the schematics, on the right-hand side here, we have also this behavior relation, this B sub B. This is a relation between behaviors, which we use to construct the relation between these abstract processes that we already saw before. And in the case of the Turing machine, that's just equality relation. And in the case of spin systems, I didn't write it here. It's a little bit complicated to define, but it expresses that the energies of the two configurations match unless they are very high. So we want the energies to match in some low energy regime. And indeed, the evaluation just takes the Turing machine and evaluates it or outputs the energy. Okay, I will skip this. This is the way you would define the abstract relation in terms of the behavioral relation. It's not so important. Okay, so now in order to find a connection between universality and what we call undecidability in some sense, we need to express undecidability in this language that we have. And for that, we use this notion. So if we take a particular morphism, which takes a program and a context and outputs a behavior, then we say that is a complete parametrization if for any possible morphism from context to behaviors on the right-hand side here, there is a program that we can supply to F that that basically generates this behavior. So if we think of the computable functions, that would be, and f being the evaluation function, it would mean that for every computable function, there is a Turing machine that computes. So that's the complete parameterization property. And then a particular simulator has what we call unreachability, which you can think of as a sort of undecidability. If evaluating that simulator with the evaluation function does not satisfy this complete parameterization property. So there are some behaviors on the right-hand side which are unreachable. They could be functions that are not computable, or problems that are undecidable, and so on. But because we don't want to refer to a particular version of undecidability, we just call it unreachable. There are unreachable behaviors in a sense. Okay, and then the theorem that we can prove, and this is following the Lawvere's fixed point theorem, but in our setting, it's quite a bit more general, is saying that if you have a particular function that takes a pair of contexts, so two inputs, they're both isomorphic to the context, generates a behavior that satisfies this complete parameterization property, then every morphism on the behaviors has what we call a quasi-fixed point. Okay, and then we can use a contrapositive of this theorem together with the following lemma. So the lemma says that if the evaluation function also satisfies this complete parameterization property and you have a universal simulator, you can in some sense pull back this complete parameterization to the composite of the evaluation function and the simulator, which together, this theorem and dilemma, we can interpret as saying that if you have a universal simulator and a morphism between behaviors that does not have a quasi-fixed point, then necessarily the evaluation function is not a complete parameterization, or in some sense, the trivial simulator has unreachability. So there are some behaviors that are not reachable. So this is a schematic picture of the implication, universal simulator, and 6.3 function, for example, a negation, implies that there are some behaviors that are unreachable. And so what does this mean? I mean, in the case of Turing machines, we defined our morphisms to be computable, so there shouldn't be any unreachable ones. Well, the way out in some sense is the fact that these morphisms are not always everywhere defined. However, we also have a version of our theorem for morphisms that are everywhere defined. So you could take the same property, but here you want to parameterize your behaviors by a program that is indeed defined, and then you just add the requirement that everything in the theorem is total, so everywhere defined, and it still works. And you get as a corollary of this somehow total fixed point theorem that there is no universal Turing machine that is total, so that helps on every input. This is not a new result, this is known. However, we get it from the fixed point theorem by adding this total restriction. If you don't have this totality of restriction, then you don't get this result that there is no universal Turing machine, of course, because every function has a non-total fixed point, which is just the undefined point. Okay, I see that I'm almost done with time. So I will just quickly mention what else we do. So besides somehow studying simulators and their universality, we also look at comparisons between different simulators, and we build a whole category of simulators with morphisms between them. They look something like this. You take a simulator, you pre-compose it by some reduction, and then there is also a post-processing on the output. And this is the kind of type of morphisms between simulators. They have to satisfy some additional properties in order to compose, and so that they preserve universality. I will not go through the details. This is kind of how the conditions look like. And what we find is a condition for a simulator to be trivial. So if you remember, at some point I was telling you that all the trivial simulators are always universal. But what we wanted to express is that there are some simulators that are universal in a non-trivial way. And what we came up with is indeed this notion that if you have a simulator that's universal in a non-trivial way, then you can somehow morph it, can find morphism to the trivial simulator, but not necessarily back. So these morphisms, in some sense, implement a kind of compression of the information. And what we prove is that the singleton simulator for universal Turing machine satisfies this. So what in our language is more parsimonious than the trivial simulator. It uses fewer resources. And we don't show it just for this simulator, but we have a few general results that guarantee such a behavior, which then...
What do you mean by singleton simulator?
Yeah, so singleton simulator, that meant that the compiler is a constant function. So in this case, it's singleton because it only uses the universal Turing machine and not any other Turing machine. And indeed, the way we show this is by kind of making use of this property of being a constant, the compiler being constant, because for the trivial simulator, it's kind of the opposite. For the trivial simulator, the compiler is an identity and somehow makes use of the full of all the targets, and this is incompatible with there being a morphism between them in one of the directions. So that's kind of the interpretation of this ordering between simulators, is that this singleton simulator for the universal Turing machine uses fewer resources. You only need to build one universal Turing machine. You don't need to build a different Turing machine for each particular function that you want to compute. Okay, so these are the details of the proof. I will just summarize now to finish on time. So in this work, we take these examples of universality, in particular these two main examples of Turing machines and spin systems, and we use them as inspiration to build this abstract language in which we can talk about universal simulators. And then we also express other instances of the framework, which are mostly at this point of mathematical interest, I would say, but we are also interested in adding to the list of examples, like additional examples that are not just within the field of mathematics, but also elsewhere in science. We prove a result that gives us necessary conditions of universality, and then we use it to show that these universal spin models cannot be finite. We define morphisms of simulators that gives us this notion of when in this universality non-trivial. We extend or generalize Lawvere's fixed point theorem to our setting, and then use it to connect this notion of unreachability to universal simulators. And also something that I didn't talk about is that we have a notion of functors between these framework instances, which we call target context functors. And they also generate corresponding functors between the simulator categories with the morphisms that I briefly flashed on the screen. Yeah, that's everything I want to tell you. Thanks for listening.
Well, thank you very much. It was a very nice talk. It's very clear. Thank you. Any questions? Let's thank our speaker first. Let's thank our speaker. Any questions? Any discussion?
Yes, testing. Can everyone hear me?
Yeah, we
hear you perfectly.
Hi. So actually,
no, James, we started hearing you. James, now we lost you.
James, now we lost you.
how about now?
Okay, try it again.
Okay, try it again.
I had a question about the Ising spin models.
Go.
Okay, good. Still coming through. So the fact that there is no finite universal Ising spin model, does that mean that individual Ising spin models are comparable to deterministic finite automata, in which to simulate the class of Turing machines using DFAs, you need infinitely sized DFAs to encode state and tape transitions? I'm trying to see where the Ising spin model fits in the computability hierarchy.
Yeah, it's a very interesting. Maybe it's better if you mute yourself. Yeah, that's right. It's an interesting question that has been at the very kind of heart of also this work and the motivation of Gemma to pursue a lot of these investigations. But it's not, at least from perspective of this framework, there's no clear answer, I would say. We, you could say there's another.
James,
Mute you.
thing off. Okay, good.
Yeah, thanks.
Sorry, Thomas.
So there is another work of Sebastian and Gemma where they find a connection between the Chomsky hierarchy of languages and spin models. They take a spin model and they use it to define a particular language that is a language of the energetic behavior of the spin model, and they classify them in the Chomsky hierarchy. So that would be a bit more in line with kind of what you are imagining, I think. In our framework that I presented here today, I would say this fact of non-existence of a finite spin model that would be universal. It's not clear to me exactly how it maps onto the Turing machines, because for the spin models, you could look at like they are like this no-go theorem. The way it works is you could just look at very simple spin models. So indeed, maybe a 1D Ising spin model. So just on a line, you have interactions between the nearest neighbors, and you still get this fact that the spectrum is unbounded. Even though the behavior of the spin model of this 1D Ising is very, very simple in a sense. And for example, in the sense of the other paper could be related to languages that are accepted by deterministic finite automata. So it's an interesting question, but I don't think I have a very concrete thing to say about it. Thanks for the question.
Any other questions?
Yeah, could you say a word about what kind of mathematics goes into the fixed point theorem?
Yeah, so the fixed point theorem, the proof is particularly reminiscent of Lawvere's proof. if we go to the statement, it uses basically some string diagram manipulations. So you can see it in terms of like a string diagrammatic equation. It's not a particularly, there's no uh, like techniques outside of category theory that we will need to use. We just interpret the go to the statement, just interpret the assumptions of the theorem, and then use them to use this complete parameterization of this function to construct a specific fixed point for G. And this fixed point, in the case of the Turing machine, you could interpret it as a kind of self-referential Turing machine that then, if you apply negation to it, generates the paradox of the liar's paradox.
Okay. Anything else?
Okay, thank you.
I was just wondering, you know, in Kolmogorov complexity, you usually compare different universal Turing machines, okay, because you want some type of comparison function. So you have a way of comparing universal Turing machines and saying which one is, what did you use the word, paucity or parsimonious?
Parsimony, yeah.
Right. So does that fit in the context? Do you know if that stuff works, if it goes through in your content, in your format?
You would have to choose a different setting, I would say. So the one that the ambient category that we have been using to express universality of Turing machines is using all computable functions. So then the reductions, there will be a reduction between any two universal Turing machines.
Right.
And so in that sense, they will be equivalent in this parsimony ordering.
Mm.
In order to express this, you would need to use a slightly different, like modified setting, which expresses this comparison.
Okay. Anyways, thank you very much. Thank the speaker again. Thomas, it was very interesting. Thank you.
Yeah, thanks for the invitation.
Right. In 2 weeks, we're going to have Alexander Thiago, who's here, or Thiago Alexander, who's here. On October 11th, he's going to talk about these. He's going to talk about internal homotopy theories, which is stuff that Alex Heller used to talk about a lot. So, and then after the week after, we'll have again on these derivators, we're going to have Michael Schulman. So that's going to be interesting. I invite you all back. Please come. And it's a pleasure. Charlotte, you're going to speak at the end of the semester. A few other people are here, and it's always a pleasure. Thank you very much, everybody. Take care. Thomas, stay in touch, all right?
Yeah, thanks.
Okay. Take care, everybody. Good night or good afternoon. Take care. Thank you for showing up.